We will now delve a little bit deeper into conditional statements as well as the types of statements they produce, which are called contrapositive, converse, and inverse. Recall from the things that we just proved in the last lecture that P implies Q is logically equivalent to not P or Q. What does that mean for the negation of the original conditional statement? So if I am going to negate the conditional, that means that I can, in fact, replace it to be able to simplify it. So not P implies Q is equivalent to not P or Q, which we can further simplify using the De Morgan's laws. So again, remember the conditional comes inside, negating everything in its path and swapping the operations. So what we end up with is not P and not Q. The double negation law says that not P is equivalent to P, and so the simplest form we can get to in this case is P and not Q. So if the direct conditional, the simplest conditional, is equivalent to not P or Q, then negating it would produce a statement that is logically equivalent to P and not Q. The order of operations we've discussed, brackets always get obeyed, but the order of operations in general is first we apply the negation, then we apply the conjunction and disjunction, and the conditional comes last. So let's take a look at the truth table for this statement. It's been a lecture or two since we've constructed truth tables, so let's remind ourselves of how to do it. Here we have the propositions P and Q in place, which means that my truth table will have columns for P and Q, and then, depending on what our expression looks like, we will fill in the following columns. So in this case, I have not P and not Q, so I will have to include those two as columns, not P, not Q. Then, in the brackets, I will have P or not Q, so this is going to be one of my other columns. And then finally, I will be able to form the entire expression here by combining already existing columns into this implication. Now again, remember that because I have P and Q, I will have four possible choices for the combinations of their truth values. And here they are. Now I'm going to construct or fill in the actual truth table column by column. Not P means I am negating the first column, so I will end up with false, false, true, true. Not Q means I'm negating the Q column, so I will have false, true, false, true. Next column we have P or not Q. So I'm looking at the column for P, and I'm looking at the column for not Q, and I am putting them together with the operation of disjunction, or. So I have true or false is going to produce true. Next up, true or true is going to be true. Next, I have false or false, which is going to be false. And finally, I have false or true, which is going to be true. And now for my final column in this case, I have that my previous column implies not P. So here I gotta be really careful about following the actual order of the implication. I am looking for this column to imply this column. So I have to read it in the correct order so that I am not doing the implication somehow backwards. This value implies this one. So true implies false. That is the case when the conditional is false. Next, I have true implies false again, so I have false one more time. Next, I have false implies true, which is going to be true. And finally, I have true implies true, which is also going to be true. And here is my table for this particular statement. Again, if we're interested in examining this table for logical equivalences, that means that we are going to be looking for two columns that are identical. And in this case, I can see that my final column is in fact identical to the column for not P. So that means that my expression P or not Q implies not P is actually equivalent to not P. Now, the other piece of definition or notation, the way that we actually call names, that is going to be useful throughout, is referring to the first and the second part of the conditional. You notice how it gets a little bit clunky to say this column implies this column, so we're going to give names to the parts of the conditional. The first part, the if part, is going to be called a hypothesis. So in the conditional P implies Q, the first part is called the hypothesis. I am hypothesizing that this is true. If something happens, then something else occurs. That first part is called a hypothesis, and the second part is called a conclusion. Now, it doesn't matter how big the actual conditional is. So, for example, in our case here, the first part of the conditional, so something to the left of the arrow, is what we call a hypothesis, and the thing to the right of the arrow is what we call a conclusion. Now, given a simple conditional implication, P implies Q, we're going to define these four of its close relatives that are derived directly from the implication itself. So if I start with P implies Q, the contrapositive is defined as not Q implies not P. So I flip the order around and I negate both sides. The converse of the original statement is defined as Q implies P, so all I did was flip the order of the hypothesis and the conclusion. The inverse means the order stayed, but each side had now been applied with negation. And finally, the negation is quite literally not P implies Q, which we have above simplified to be P or not Q. Now, it is interesting to explore the relationships between these four: implication, contrapositive, converse, and inverse. The negation, of course, is going to be just the exact opposite of the original. But amongst four of these, the question to ask is, are any of them logically equivalent or maybe logically opposite of each other? Now, there are two ways of going about seeing whether that's the case. We can construct the truth table, which what this example is asking for, or we can apply logical equivalences rules from a few pages back. I will leave that second way for you to explore, and I strongly encourage you to do so because, again, it gets you practicing laws with a very particular purpose. But in this example, we're going to construct the truth table for the four forms that all involve the implication. Now, they all involve P and Q, so my truth table will contain P and Q columns. And then they also all involve the implication, but also, before we get to the implication, I gotta notice that there is the nots on some of them. So I'm going to have the column for not P, I'm going to have a column for not Q, and then I'm going to proceed in order that I was given. No particular order. I have the original implication, P implies Q. I have the contrapositive, so not Q implies not P. I have the inverse, or sorry, the converse, I suppose, comes first in that list. Q implies P. And finally, I have the inverse. So not P implies not Q. Excellent. How do we go about filling this out? Well, first I'm going to start with assigning all possible combinations of values to P and Q. Here we go. Then the columns for not P and not Q are fairly straightforward. Not P is the negation of the column for P. Not Q is the negation for the column for Q. So this is nothing that we haven't seen before. So I can fill these out fairly quickly. Next up, I have a conditional. P implies Q. So I'm looking at true implies true, which is true, followed by true implies false, which is false. False implies true, or false implies false are both true statements. Now we're really into the weeds here because we gotta use our negation columns and also be sure to actually keep the proper order. Not Q is my hypothesis, so that's where I'm gonna start, and not P is my conclusion, so that's where I'm gonna go. So my order goes from here to here. Not Q implies not P. False implies false is true. Next up is true implies false. That's my case of a broken promise, so that's false. False implies true is true. And finally, true implies true is also true. Great. Next up, we have the converse. Q implies P. So I'm looking at my two original columns, but instead of going P implies Q, I consider Q implies P. So I'm going backwards in this direction. And I notice that my case of a broken promise occurs in the third row here, where true implies false the one time. So I'm going to have false here and true everywhere else. And then finally, I have the inverse. Not P implies not Q. So I'm focusing in on these two columns and seeing where I will have the falses, if there's more than one, in this case. So are any of these cases true implies false? And yes, I spot it in the third row here and nowhere else. So this is where I'm going to have my false value, and it's going to be true everywhere else. Now, what do we notice? Well, I can clearly see that these two columns are identical and these two columns are identical. Let's take a look at these two first. See how they have the exact same truth values? Remember that that means that my actual expressions are logically equivalent. So these two are the same column, and these two are also the same column. So what that actually means is that P implies Q is logically equivalent to the contrapositive, not Q implies not P, and this means that Q implying P is logically equivalent to not P implies not Q. These are the two rules that are going to come in handy all the time. However, if you actually, again, sort of squint a little bit, you will notice that these are not two separate rules. They're actually the same rule. They're just the contrapositive. What the contrapositive is saying, that the hypothesis implies the conclusion, is equivalent to saying that not the conclusion implies not the original hypothesis. And that's the same exact structure here. The hypothesis implies the conclusion, if not conclusion, implies not hypothesis. They're just relabeled. What we are calling P here is called Q in the second line, and what was called Q is called P now. Okay? The key thing to remember then is the logical equivalence of the simple conditional to its contrapositive. This might seem a little bit unnatural, and the mistake that everybody always makes in terms of their intuition is to actually think that the implication is equivalent to its converse, which, once you translate it to words, doesn't actually work, but that's a logical trap that a lot of people seem to fall into. If it's sunny today, then we will go to the beach is not at all the same as if we're going to the beach, then it's sunny today. After all, we might go to the beach even if it's overcast. The contrapositive is the one that is guaranteed to be equivalent to the conditional based on our truth table showcase here. Now, in order to further solidify what contrapositive, converse, inverse, and negation mean, we will take an English sentence and then write down the corresponding relative of the implication for them. So the sentence I'm going to start with is, if I had $1 million, I'd buy you a fur coat, straight from the Bare Naked Ladies song. This is going to be my hypothesis, and this is going to be my conclusion. So if you wish to label them, what we have here is P implies Q, where P is I have $1 million and Q is I bought you a fur coat. Going through the 4 different implication variations, what are we going to have? So let's start with the contrapositive. Contrapositive says that one must not only flip the order, but also negate them both. So I'm going to move this sentence around and negate both sides of it. Maybe let me write down what the contrapositive actually is. Not Q implies not P. So what are we going to have in this case? In this case, we're going to have, if I didn't buy you a fur coat, that means I don't have $1 million. The next up on our list was the converse. The converse is defined as simply switching the order. So instead of P implies Q, I'm going to have Q implies P. In terms of English here, that means that if I bought you a fur coat, that means that I had $1 million. Notice how that is really not equivalent to the original statement. The original statement starts with an assumption that I have $1 million, in which case I will buy you a fur coat. But just because I bought you a fur coat doesn't guarantee that I had the money to begin with. Next up is the inverse. The inverse is defined as not Q implies not P implies not Q. So we're keeping the order the same, but we are in fact negating both sides. If I don't have $1 million, I will not buy you a fur coat. And it's becoming a little clearer why these two statements are in fact equivalent as per our truth table. If I did buy you a fur coat, I had $1 million. If I don't have $1 million, I won't buy you a fur coat. Think about that for a second and try to persuade yourself of the fact that that is actually the same thing. And then finally, we have a negation. Again, negation is actually not P implies Q, or in the simplified form, it is P and not Q. So the negation of the conditional is actually not a conditional at all. It's an and. So what do we have here? We have P. So in this case, I have $1 million. And not Q, I didn't buy you a fur coat. And it's kind of clear why that's equivalent to the first one, isn't it? This one says, it's a promise. If I have $1 million, I'd buy you a fur coat. And the negation kind of says that you're specifically disobeying that promise. I have $1 million and I did not buy you a fur coat. You have completely denied the conclusion here. Now, in order to practice a little bit more, I encourage you to do the same with the other two sentences, where you see what the original conditional is, and then you write out all the possible variations of it, trying to think about why the contrapositive is equivalent to the original and the converse is equivalent to the inverse. Now, as I mentioned earlier, the conditional and its contrapositive are the two main implication forms that we care about. Everything else can actually be derived through them. So in order for us to solidify the naming of them as implication or conditional and the contrapositive, let's take a look at some of these examples. So in this question, we are asked to determine whether each statement is true or false. It is possible for an implication and its contrapositive to have different truth values. Think about that for a second. Do you think that that statement is true, or do you think that that is false? I have an implication, and I have the contrapositive. Is it possible that these two have different truth values? Well, they are logically equivalent, which by definition means that within the truth table, the columns that correspond to each one are identical. So no, that is not possible because they are logically equivalent. Next up we have, if P implies Q is a contradiction, then so is its contrapositive. Remember, the contradiction is a statement that is false independent of what the truth values of its components are. So contradiction essentially means it's always false. So what this is saying is, if the implication is false, then so is its contrapositive. What do you think? Is that true or is it not? Well, as we've just discussed, the implication and its contrapositive are logically equivalent, which means that if one of them is false, then so is the other. So I literally have the exact same justification as in the question above, but now a different conclusion. Yes, if one has a truth value that is false, then so will the other, because the truth values have to be identical. There are truth values for P and Q such that P implies Q and Q implies P are both false. How do you think we're going to go about doing this one? It's specifically asking, are there any truth values for P and Q so that the conditional and the converse are actually both false? Since these statements are not logically equivalent, it's not going to be a quick yes or no. How do we determine if there are any truth values such that something holds? We look at the truth table. And luckily, we actually have a truth table containing both of these statements, P implies Q and Q implies P, right on the previous page. The question is asking about, are there any values where both of these are false? And we can see that, nope, there is not a single row where both of these are in fact false. So the answer here is going to be no. See the truth table on the previous page. Or rather, in general, you can see any truth table for P and Q implies P. If two statements are logically equivalent, then so are their negations. Logically equivalent means that their truth values are identical in the entire column. If we negate both of them, we flip everything, so the negations will have the exact opposite values, but they will be exact opposite in exactly the same way. So I'm going to write a short yes, and you can make up a sentence for the justification yourself. Next up, what do we have? We have the actual statement that this compound proposition is a contradiction. How are we going to figure that out? Again, remember, the contradiction means that it is false independent of P and Q. And as always, there's two ways of approaching this. We can construct a truth table, or we can employ the laws of logical equivalences. Since we've already constructed a truth table once today, let's go the logical equivalences route. So we're going to take this and we're going to try to simplify it. If it's indeed a contradiction, at the end of our simplifications, we should see false. If it's not a contradiction, we will find something else. So what is the first thing we can do to simplify things here? Well, looking at the general structure, I can see two sets of brackets, and one of them has a negation in front of it. So the first thing I'm going to do is to bring this negation into the brackets using the De Morgan's laws. So I'm not going to change the first portion, but I will change the next one. So I'm going to have not P and not Q. And again, I'm going to include my justifications here by De Morgan's laws. Next, I can see that not P is going to be simplified by the double negation law. So I can rewrite this as P and not Q using the double negation law. I should also point out, actually, that just because I follow a specific way to apply logical equivalence doesn't mean it's the only way. You could have very well somehow decided not to apply the double negation law here and carry on forward in a different direction. As long as every single step that you use is actually justifiable as a logical equivalence, you are proceeding in a valid way. Now, what else can I do here? So I can see that my operations aren't exactly the way that the distributive law would have them. These two are the same, but then this one is different. So I can't distribute it out. Maybe I can use an associative law to somehow group these together. I'm going to group them together in this way so that I can maybe somehow deal with the p's on the inside later using the distributive law. Okay, so I am going to actually sort of skip a step here and maybe introduce the brackets at this point so I can save myself a little bit of writing. I'm going to enclose these two in brackets, and I'm going to add associative law here as the thing that I'm applying. Excellent. Once I do that, I can see that I have two operations that are different, so I can actually use distributive law on this portion. So using distributive law, what do I have? I'm going to have not P and P, or Q and P. These are my square brackets and not Q. Now, at this point, you might be thinking, this is getting a little out of hand. These expressions were getting smaller and now they're getting longer again. Now, patience is a virtue, and we can see that things are going to start getting simplified very soon. I have not P and P, which I know is going to be false, and I'm going to leave it up to you to find the law that actually claims that that is the case. There's also another law that says that false or something is going to be just that something. So now I have that my entire square bracket reduces to just this one expression here, Q and P. And I have the not Q from outside of the square brackets. Okay, so again, I skipped two laws down here, find their names, and actually fill that information out. Once I get down here, I would really like to get Q and not Q to be next to each other. And the law that allows me to do that is also one in the table. Look up its name so you know what it's called. I'm going to have Q and not Q and P. And now I am actually at the final stage. Q and not Q is always false. False and anything is always false. So my entire expression is equivalent to false, which means that it is a contradiction. So yes, this is in fact correct. Again, I've skipped labeling a bunch of laws here so that you can look back at the table and fill out that missing information yourself. The key here is to learn to use the table effectively. And once more, I would like to emphasize the fact that this is not the only way to proceed through this example. Maybe you can find a better way to actually shorten this argument and think about how to do it. Next, let's discuss the necessary and sufficient conditions as a way to actually apply implication and its converse. P is sufficient for Q means P implies Q. P is necessary for Q means Q implies P. Let's now go through some examples to see how we can connect the logical statements to the colloquial English words that we're so used to using. And we're actually going to see that they mean the same thing in logic as they do in everyday life. So for the first example, we have, you must be at least 18 to get a driver's license. First of all, there's two pieces of information in this statement: the age and the fact that one does or does not have a driver's license. So let's label them. Being at least 18, we're going to call P, and getting a driver's license, we're going to call Q. And the idea here is to figure out, does this mean that P implies Q or does this mean that Q implies P? Do you think that it is necessary to be 18 to get a driver's license? Or do you think that it's sufficient to be 18 to get a driver's license? My claim is that it's necessary, but not sufficient. Why is that the case? In order to get a driver's license, it is an absolutely necessary condition that you are of the right age. But just because you're 18 does not guarantee that you will immediately get a driver's license. So the age factor is not sufficient for the obtaining of the driver's license. Now, if we're talking about the necessary condition, we are talking about the form Q implies P. So in our case, that means if you have a license, you are at least 18. And once again, just because you are 18 does not guarantee that you actually have a driver's license. So the conditional in the other direction will certainly not be correct. Let's take a look at the next example. All dog owners are happy. Again, there's two parts to it, being a dog owner and being happy. So we're trying to figure out, is the dog ownership necessary or sufficient condition for happiness? Is it necessary to have a dog to be happy? Is it sufficient to have a dog to be happy? Think about that in terms of what the statement actually says, not what you believe about in the world. This one says that all dog owners are happy. All the people that have dogs are in fact happy. So is it necessary to have a dog to be happy, or is it sufficient to have a dog to be happy? My claim is that this statement is sufficient, but not necessary. Let's take a look at it again. It says that all the dog owners are happy people. So as long as you own a dog, you are certainly happy. However, it says nothing about people's happiness that don't have dogs. It doesn't exclude somebody who does not have a dog from being happy. So it's sufficient, but it's most certainly not necessary to have a dog in order to be happy. The hardness of analyzing these statements is to be able to abstract from what you believe about in the world and only use the actual information provided. In this case, the conditional that corresponds to it will be, if you have a dog, you are guaranteed to be a happy person. What happens if we combine the necessary and sufficient? P is sufficient for Q means that P implies Q, and P is necessary for Q means that Q implies P. We can in fact construct a truth table for this expression and figure out what it is equivalent to. Let's take a look what we have. P and Q values. I encourage you to pause the video and actually go through the motions yourself, because once again, this will provide some practice with determining the truth values of the conditional and the converse and how to actually combine everything together. So we're going to have the 4 possible truth-false combinations for P and for Q. P implies Q will be only false in this one case. Q implies P, again, remember the order matters. This is the hypothesis, this is the conclusion. So we will be going in this direction, and the only false, the only broken promise occurs in line 3 here. So we have false here. We can fill the rest of them out with truths. And my last column is going to be the combination of the two. So P implies Q and Q implies P. I'm going to AND both of these columns together. Now remember, AND is only true if both of the statements are true. So we're going to have true and true here, false and true, true and false, true and true. I can see that the first and the last lines are going to be true, and the other ones are going to be false. Taking a peek at this last column here, and thinking about what the corresponding P and Q values are, does this look like another equivalence that is recognizable? If you stare at it long enough, you might actually remember that this is exactly what the biconditional looks like. And in fact, this is where the name comes from. P, if and only if Q. If P, then Q, if Q, then P. if and only if, will give us the biconditional. Now remember that the biconditional, being the logical equality, so to speak, is true only in the cases where the P and the Q values are equal, be them true or false, simply they have to be the same as each other. So I have that the necessary and sufficient is equivalent to the actual biconditional. So let's write this down. This, we will read it as P if and only if Q, and this is in fact equivalent to our biconditional, where the arrow points in both directions as it does in this expression here. So far, we've spent quite a bit of time doing truth tables, logical equivalences, logical laws, as well as working with conditionals. This page has a few more exercises to allow us to practice those skills. So the first example here asks us to fill in the laws which were used in the simplification of this particular expression. Now, I told you that it is handy to have the table of laws on hand in case you want to actually refer to it. So here is my copy, my digital copy right here. How do we go from row 1 to row 2 right here? Notice that I had a negation on the outside and then I no longer do, which means that this was most likely the application of De Morgan's laws, and let's check whether that was actually applied properly. If I negate everything throughout, including the operation, then it looks like that was actually properly done. So this was the application of De Morgan's laws. For the next line, we have a similar happening. So we had a negative out here, and then it was brought into the brackets. Again, we can check to make sure that it was done properly, and in fact it was. So this is also the De Morgan's law. Next up, we have the simplification from this line to this line. This double negation went away, and not P turned into just P. This is the double negation law. Now, these are the ones that you probably already remember because we have seen quite a few of them. But some of them might not be as familiar because they simply get applied a little less often. So what is the difference between this line and the next line? The operations didn't happen, the negation stayed the same, but the order of the P and the not Q inside the bracket changed. The order, the law that allows us to change the order is called commutative law. In the next line, we went from this to this. Notice that the operations were opposite and we have expanded out the brackets. So this is a clear application of the distributive law. Next up, we've kept the second bracket but simplified the first one from not P and P to false. And the law that corresponds to that in our table is the negation law. And then finally, the last line here, we went from false or something just to that something. And the law that allows us to do that is this identity law right here. So if this was an exam and the actual question asked to simplify this expression, including the laws as justification for why you can carry on from one line to the next is absolutely essential and crucial. If you were checking someone's argument, seeing what laws they applied will allow you to figure out if they did it correctly or not. So don't forget to actually label each step in your simplification with the corresponding laws. Now, what do we have in the next example here? We're back to practicing a little bit with the conditionals. Rewrite the following statements in the if-then format and also write their contrapositives. For the first one, we have being born in Canada is sufficient to obtain a Canadian citizenship. Remember from the previous page, the sufficient and the necessary both corresponded to different formats of the conditional. The sufficient here connects two portions of the sentence. Being born in Canada, which, for example, we can call P, and obtaining Canadian citizenship, which we can call Q. And now we can both logic it out in plain English, or we can simply flip back and see P is sufficient for Q translates to what if and then statement? It translates into P implies Q. Now let's actually see if we believe that that's the case. So what this is saying is this statement is equivalent to saying if you're born in Canada, then you will obtain Canadian citizenship. Does that seem like it's equivalent? Or do you think it's the other way around? If you have Canadian citizenship, then you were born in Canada. Well, for many of us who are immigrants, we know that the opposite direction does not hold. I have a Canadian citizenship, but I was not born in Canada. So while being born in Canada is certainly sufficient, it is absolutely not necessary. There's other ways of obtaining Canadian citizenship. So the true statement in the if-then format is if you're born in Canada, then you can obtain, or then you have Canadian citizenship. Now, the contrapositive to the statement, remember, we have to flip the order and also negate both of them. If you do not have a Canadian citizenship, you were not born in Canada. Next up, we have it is necessary to pass Math 111 to get into Math 112. Again, we can simply label the corresponding parts of the statement. Passing 111 can correspond to statement P, and getting into Math 112 can correspond to the statement Q. So this says that P, passing Math 11, is necessary for Q. If we look back on the previous page, we will see that that corresponds to Q implies P. But once again, we can see if we can actually reason it out. What this will say then is, if you are in Math 112, then you passed Math 111. Well, it was necessary to do so, so you must have in order to get in. If you mistakenly did it the opposite direction, would the actual statement make sense? So we would have that if you passed Math 111, then you got into Math 112. Is that true? Well, just passing Math 111 might not be sufficient. There might be gigantic waiting lists in Math 112 that semester, or it might not work for your schedule. So just passing Math 111 is not sufficient to get into Math 12, but it is certainly necessary. Let's write this out. Great. Moving right along, we have determining the hypothesis and the conclusion in each of the following implications. You are in Canada if you are in British Columbia. So the if here starts with the second part of the sentence, and we can in fact rewrite it without changing the meaning at all. If you are in British Columbia, then you are in Canada, which means that this is going to be our hypothesis, and being in Canada is going to be our conclusion. Now, next up is the statement with only if. So this is getting a little bit trickier. Maybe let me highlight the fact that this was if, and the next one is going to be only if. Bill goes to the party only if Greta goes to the party. The only way that Bill will go to the party is if Greta also goes there. Is it necessary for Greta to go to the party for Bill to be there, or is it sufficient for Greta to go to the party for Bill to be there? Think about that. Which way will it go? My claim is that Bill going to the party is the hypothesis, and Greta going to the party is in fact the conclusion. So if I were to rewrite it in the if-then form, it would say if Bill goes to the party, then Greta is also there. It is absolutely necessary that Greta is there in order for Bill to also be there. For a number to be even, it is sufficient that it's divisible by 2. So now we have yet another form of the if-then statement, the sufficient factor. What do we have here now? I mean, looking back up, you can also cheat a little bit and see what the sufficient actually corresponds to, right? We've already had the example just right above there. So we have that if the number is even, which means that this is our hypothesis, then it's divisible by 2. And this is our conclusion. Now, in this particular case, in fact, it is both sufficient and necessary. If the number is divisible by 2, then it is what we call even. So this is, in fact, an if and only if statement. Moving along to writing more English statements in terms of logical, let's see what we have here. We're asked to write the statement in symbolical form and then determine if they're logically equivalent. If you paid full price, you did not buy it at outlets. You didn't buy it at outlets, or you paid full price. So we, in order to write everything in symbolic form, first of all have to actually determine what our propositions are going to be. It's clear that I am interested in something about buying things full price and something about buying it at the outlets. So I'm going to let P correspond to paying full price, and I'm going to let Q correspond to buy it at outlets. Then what is my first statement says here in terms of P and Q? If you paid full price, you did not buy it at outlets. So what I have here is if P, then not Q. Whereas the second one says you didn't buy it at outlets or you paid full price. So what I have here is didn't buy it at outlets, not Q, or you paid full price, P. Are these two statements equivalent? What are the ways to figure out whether something is logically equivalent to something else? There's generally just two approaches. We can construct the truth table, P, Q, the truth values, and so on, or we can apply logical equivalence laws. I invite you to try both approaches to figure out which one works best for you, and in fact, try to practice the one that you've been avoiding more. Let's take a look at part B here. If it walks like a duck and it talks like a duck, then it is a duck. If it does not walk like a duck and it does not talk like a duck, then it is not a duck. So what are the sub-propositions here? I'm going to have walking like a duck, and you know what? Let me actually label them somehow corresponding to the actual words. So W will correspond to walk like a duck. Then T will correspond to talk like a duck. And D will correspond to is a duck. Now, let's translate what we see to the statements using W, T, and D. If it walks like a duck and it talks like a duck, then it is a duck. That is going to be my first sentence. The second one says, if it does not walk like a duck and it does not talk like a duck, then it is not a duck. Okay? Again, if we are to figure out whether these two statements are logically equivalent or not, we have two choices. We can create a truth table. In this case, it will involve 3 variables and therefore 8 rows. Or we can try to apply logical equivalences to see if these two are in fact the same. Now, because both of these are actually conditional statements, we already know quite a bit about equivalences of conditional statements. So maybe we can leverage our knowledge of contrapositive, converse, and inverse to justify whether these are equivalent or not. I leave that up to you for extra practice, but again, try to practice something you haven't practiced quite as much. If you've been avoiding truth tables, do one of those. If you've been avoiding applying logical laws, then do one of those.